Welcome. This is a short video on the chi-square test. Chi-square is a non-parametric test. That means that it does not share assumptions such as the assumption of normality or homogeneity of variances. And there are actually two different chi-square tests that I'm going to cover briefly. One is what's called the goodness fit test, which is to determine whether observed proportions in a single variable. So in a categorical variable to whether they significantly differ from theoretically expected proportions. So if you expect there to be, for instance, a 50-50 split between two groups, and you actually have a total sample size of 70 and you have a 40-30 split, the question is whether or not that's significantly different from what you would expect under the null of a 50-50 split. And the second type of test is called the test of independence, which is to determine whether or not there's a systematic relationship in membership between two categorical variables. So for instance, if you have ice cream preference and personality type in terms of introversion, extroversion, whether there's a relationship between ice cream preference and being extroverted. So this is used mostly for categorical data and ranked data, not for interval or higher or continuous variables. So this pretty much says what I just said. You have the chi-square goodness of fit test. So for instance, if you know that 37% of adults consider themselves Republicans, 18% independent, and 44% Democratic, and you compared that to sample data that you had actually gathered from, for instance, New York City, would the proportions match the expected proportions from national data? And the independence test or test of association would be, is there a relationship between smoking? Yes, no. And coronary heart disease? Yes, no. Two things that are categorically measured. So we have our hypothesis tests, our hypothesis statements. For the goodness of fit test, we would say the null hypothesis was that the observed distribution fits the expected distribution. And for the alternative, we would say the observed distribution does not fit. For the chi-square test of independence, we would say the variables are independent. There's, for instance, no relationship between smoking and coronary heart disease, or the variables are statistically dependent. There is a relationship. The assumptions, which I believe I will state a little bit more later, are that the sample is chosen randomly and the scores are independent. Each subject is only allowed one value. There are no overlapping categories. The chi-square distribution is like the F and the T, a category, a family of distributions. And the shape of the chi-square distribution varies according to degrees of freedom, just as with those others. Degrees of freedom in chi-square is determined by the number of categories. So the null hypothesis steps for chi-square are very similar with other tests. There are a little bit fewer of them. So you state the null and the alternative. Chi-square is always non-directional. You decide the type of test. Is chi-square the appropriate kind of test? You establish the level of significance and determine a critical value. You calculate the test statistic and you make a decision about the null hypothesis. So we're going to start with the goodness of fit test and go through steps 1 and 2 rather quickly. So we have a research question. On published true-false items, does true occur in equal proportion to false as the correct response? And for our data, or I'm sorry, I'll go straight over to the right to the hypothesis. This is a goodness of fit test. The observed distribution fits the expected. So we're going to gather data, our observations, and we have an expectation, which we'll go to in just a minute. And the alternative hypothesis, the observed distribution, does not fit the expected. So for our data, we're going to randomly select 90 true false items from a publisher's item bank for a statistics course, let's say. And we find when we collect that data that 55 of the 90 items are true items and 35 are false. So we want to know whether or not that fits our theoretical hypothesis that they would occur in equal proportions. So how do we know, step 2, if chi-square is appropriate? The data are categorical, true and false. The data are independent of one another, and the categories are non-overlapping. Nothing can be true and at the same time false. And there are no empty cells. There are cases that are true. There are cases that are false. Some other time we may get into chi-square can be inappropriate to run if you have any very small sample size or a very small expected value. But we're not going to run into that this video. So our critical statistic, as I said, critical statistic is determined by the number of categories because your degrees of freedom have to do with categories. So how many categories do you have? You have 2, which means that J minus 1 is 1. It's basically the fewest degrees of freedom you can possibly have for a chi-square. We're going to assume that alpha is 0.05. I'm just taking that as a given, in which case with 1 degree of freedom, all the way over there on the left where it says nu is 1, and going over to the column where alpha is 0.05, we see a critical value of 3.84. So that's our critical value. The chi-square distribution can be found in most textbooks. Now we have our formula. Step 4, calculating the chi-square. So the chi-square, let's look within the parentheses first. The numerator is the observed minus the expected squared. So we've seen things like this before. The deviation of our actual observed values from the expected value. The thing is going to be figuring out what that expected value is. But you take those deviations, you square them, you divide them by the expected value, and this is for each category, and you sum that. So we've got 2 categories. We're going to have 2 terms that we sum. And then you multiply that by the total number of cases. So let's look at our example. We have these published true false items, and we have 90 items, 55 plus 35. And we want to find out whether they fit our expectations. First thing we're going to do is we're going to convert those to proportions. You don't have to convert them to proportions, but at some point, it's much simpler to work with. So that's what we're going to do. It's certainly for hand calculations. So we convert them to proportions, and we say we've got 61% or 0.61% of the cases, 0.61 cases are true and 39% are false. So we got to compare to what's expected under the null hypothesis. Remember, under the null hypothesis, there's no difference between what we observe and what we expect. So then the question is, number 1, what is the expected proportion for each of the 2 categories if the keying of items is random? Does the true occur in equal proportion? Well, if the 2 occur in equal proportion or they're random, then it should be 50-50. So that's what our expected values are going to be. The expected value for true and the expected value for false will each be 50%. Now we're going to compare that to the observed proportions. 61 compared to 50%, and 39% compared to 50%. And we're going to go through our formula with those numbers. So, calculating chi-square. I've rewritten these things as in decimal format, and the first row you see is the full formula. The second is writing it out. Okay, so the first term in the numerator is our observed values, 0.6111 or 61%, minus our expected value, 0.50, 50%, the null expectation. The difference between those two squared. Plus, because we're going to end up summing them, I really should have left out that summation sign, but I left it in, I'm sorry. The difference between the observed for false, which is 0.3889, and the expected for false, 0.50, and that term squared. The expected value for each group is the same, so I've just put the entire term over 0.50. I could have written 0.6111 minus 0.50 squared over 50 plus 0.3889 minus 0.50 squared over 50 as two separate terms, but I put them all over the same denominator because the denominator was common. So I work out that numerator, it's 0.0123 plus 0.0123. Because that's after I squared them. So 0.6111 minus 0.50 squared is 0.01123. Take the sum of those two divided by 50, and over to the left, on the right side of the equation, you multiply by 90. You multiply by the total number of cases in the sample, which is 90. So you multiply 90 times the sum of 0.0123 and 0.0123 divided by 50, and the result of that is 4.44. So that's your calculated chi-square for this goodness of fit test. Now we make our decision. So on the published, sorry for the typo, true false items, does true occur in equal proportion? Our critical value is 3.84. Our obtained value is 4.44. Our obtained is greater than our critical value, and therefore we reject the null hypothesis. The distribution of true false items in the publisher's item bank is not what we would be expected by chance. So that's the goodness of fit test. The second type of test is the test of association. So for instance, we want to know, is there a relationship between self-monitoring during problem solving and training and self-regulation? So we've got two categorical variables now. Do people self-monitor or not? Yes or no? And have they been trained in self-regulation or not? Yes or no? Our null hypothesis is there's no relationship. The two variables are statistically independent of one another. Our alternative is that they are statistically dependent. There is a relationship between whether or not you've been trained in self-regulation and whether or not you self-monitor during problem solving. We've got 100 students. We assigned them in equal numbers to one of two conditions in an experiment. One condition received instruction in using self-regulated learning practices to monitor their own work on computer science problems. After the intervention, both groups were observed to see if they checked their solutions while solving computer problems. Is chi-square appropriate? So we've got our step one, our hypotheses. Step two, is this the right test? The data are categorical. Yes. They're independent and non-overlapping. No one appears twice. No one belongs to more than one cell at the same time. And no cell is empty. So yes, we're going to go ahead with chi-square. Now we have to find our degrees of freedom in order to find our critical statistic. So degrees of freedom for the test of independence is the product of the two group sizes minus one each. Okay, so the degrees of freedom for each group. And in this case, so we can only use J once. So we're going to use J for the number of categories in the first group and K for the number of categories in the second group. Now, each group has only two categories. So J minus 1 is 1, 2 minus 1, and K minus 1 is 1, 2 minus 1. So 1 times 1 is 1. So we're going to have the same degrees of freedom as we did in the previous example. 1 degree of freedom with alpha of 0.05 is going to give us a critical statistic of 3.84. So now we have our we're assuming alpha of 0.05. We have our critical statistic, and we go on to calculate the chi-square for the test of independence. So it's a little bit more complicated because you have to have the marginal values. And so to think a little bit about this, if you expected that there was no relationship between checking and being in a condition, then if overall, okay, so regardless of what group people were in, 62 people checked, 62 out of the 100 people checked, or I'm sorry, 62 out of the 100 people did not check. So you look down that checking column, and where it says 0, that means they didn't check. 62 of them did not check. 38 of them did check. You see that where I've circled in red? Now, if those marginal values were evenly distributed between the control and the experimental group, you'd expect, oh, 62 people didn't check, then it should be 31, half of the 62 in the control group didn't check, and 31 in the experimental group didn't check. If 38 people checked, got a 1 for checking, yes, they checked, then I would expect if there's no relationship between condition and checking, then of the 38 who checked, 19 would be in control and the other 19 would be in experiment. In that case, it would be an even balance on checking, regardless of group. So those are my expected values, are going to be 19 for yes, I checked, and 31 for no, I didn't check. Okay, so I've written these as proportions. 0.36 in the control, didn't check. 0.26 in the experiment, didn't check. 0.14 in the control, did check. 0.24 in the control in the experiment, did check. So assuming there's no relationship between the condition and checking, null, we expect equal rates of checking in both groups. If students in general only check 38% of the time, that rate should be evenly distributed. It's not. They're not both 0.19. One is 0.14 and one is 0.24. So we want to see whether or not that's statistically significant. So now we're going to work out our numerator. So given that 62% overall didn't check, then if there's no relationship, we think 31% or 0.31 will be in the controlled no checking group, and the other 0.31 will be in the experiment no checking group. So those are our expected values for those cells. And we're going to look at the deviation of those expected values for to calculate our numerators. So we take the no checking control, 36% of control, I'm sorry, 36% of the whole didn't, I'm sorry, I just got, so 0.36 minus the expected 0.31. 0.36 is the observed value, 0.31 is the expected value, and you square that, and that's your first deviation of the observed from the expected, squared. First squared deviation of the observed from the expected. The second one is the control who checked, 0.14 minus 0.19 squared. Third term, and so on. And we are going to divide each of them by their expected value. So I'll show that worked out next. So you take each of those squared deviations and you divide it by its expected value. For the no checking condition, the expectations are half of that 62%, which is 0.31 and 0.31. For the checking condition or the checking event, the expectation is 38%, so 0.19, 0.19, that's the expectation is set by the null hypothesis that those will be the same. And we sum all those values. So 0.36 minus 0.31 squared divided by 0.31 is 0.00806. And you have those four values and you sum them all. And then the last thing so the sum of those values is 0.04244, and you multiply by the number of cases, that n. So that's 100 times 0.04244. Your chi-square is 4.24. Our decision, is there a relationship? There's your setup, your data. Your critical statistic was 3.84. Your obtained statistic was 4.24. Your obtained is greater than your critical. You reject the null hypothesis. There's a significant relationship between training and checking. Those in the experimental condition checked proportionally more often than those in control. And that's all, folks.